Good. Okay, so let's begin. This week we have Lada Peksova, who's going to be talking today about quantum homotopy algebras and other things. And the homological perturbation lemma.
Yeah, thank you. Sorry about switching the side. So it's a part of my thesis, but it's ongoing work with Branyo, Jurcho, Martin Dulbeck, and Janči Pullman. So it's like an article which is still in the process. So some of the details are, in the end, are not like solved yet. So, but I will like talk about the beginning, and there everything is basically solved. So I will start with the motivational example, which will be something which a lot of you probably already know, and it will be for closed strings. And then I will try to show what we do for the open strings, that we are trying to do something analogical. And then I will show how some constructions which were done before for the closed strings can be now done also for the open strings. So the open in the closed strings, when you think about like how to describe them, there is like two levels how to do it. On the geometrical level, you can be thinking about having the singular chain complexes of Riemann surfaces, of modular homomorphism classes of Riemann surfaces, which are orientable, and you have some possibly non-trivial genus, and there's some set of punctures. So here the punctures are denoted by these disks. Do you see the mouse or not?
Yes.
Yes, so here the punctures are denoted by the disks, but in general it's like a puncture on the interior. And on this geometrical interpretation, you have also the structure where you are saying that you can either glue two surfaces together, like identifying two punctures of two different surfaces, or you can make some self-gluing where you identify two punctures of one surface and possibly raise the genus. And to these closed strings, you can also assign some algebraic version of this picture. And so then you have some formal functions, which are just like symmetric tensor powers of some vector space V, or the graded dual of the vector space V. And on this vector space, you have the odd symplectic form of degree -1. So you can form a second order operator, which we will call BV Laplacian, and some bracket, and they will correspond to what is on the geometrical picture. The self-gluing will be given by the Laplacian, and the gluing of two surfaces will be given by the bracket. And you can quickly realize that you have Batalin-Vilkovisky algebra. So you, on this vector space, Fun V, the formal functions, you have some graded commutative product. You have some bracket, which is acting similarly like in the Lie algebras, but there is some non-trivial shift. And you have a square zero operator, this BV Laplacian, which is of degree 1. And there is some compatibility between the BV Laplacian is not a differential, because there is like the term on the right hand side, the last one, is basically telling you what is making this BV Laplacian not to be a differential, like there is some problem. And you not only have the Batalin-Vilkovisky algebra, but you also get in this picture the solution of quantum mastery equation. And for the closed strings, on the geometrical level, you know what it means to like decompose these modular spaces of Riemann surfaces. And on the algebraical version, it means that you get some action, which will be gauge invariant, and it will satisfy this quantum mastery equation, where again you have this BV Laplacian and the BV bracket. And if you look on the components of this action on each M and G, like the number of punctures or correspondingly the powers of the vector space, and the G, which corresponds to the either H bar powers or to the geometrical genus of the surfaces, you can rewrite these components of the action as some symmetrical functions, LGN. And if you look on what these functions satisfy, you realize that the action actually encodes you the quantum L infinity algebra. So the quantum mastery equation could be equivalently described as this equation where you have the term which corresponds to the Laplacian and the term which corresponds to the bracket. Here you use, in the first one, you use the pairing from the symplectic form. So this was what was already known for the closed strings, and now we can ask, can we do the same process for the open strings? So this time we would have, on the geometrical level, the homomorphism classes of compact connected surfaces, Riemann surfaces with some genus G, again some set of punctures, but this time the punctures will be on the boundaries of the Riemann surfaces. And you again will have some gluing between two surfaces and self-gluing, which will correspond to identifying the puncture of one boundary, that's puncture from other boundary, or with the self-gluing, it could be also from the same boundary. And before, in the closed strings, we can like freely permute the punctures, but here now in the open case, we cannot freely permute the punctures, but when we have punctures on one boundary and we act with a cyclic permutation, it will be trivial. We will get again the same cycle. So there are some permutations which will be acting trivially, as some will not. And we want to describe this structure on the algebraical level. So we have the geometrical picture, and now is the question how to make the algebraical as before. And what one can realize is that we actually have there underlying a structure of modular operads. So the geometrical could be seen as you have the operad morphism from some Feynman transform of modular operad to the chains on moduli spaces. And these formal functions can be seen as that you have the operad morphism to some endomorphism operad. So this would be the algebraical level. And now is a question, what could we do to capture the whole structure, the Batalin-Vilkovisky structure on this endomorphism operad or on this geometrical level? And there are some ideas, but the question is like, can we use the modular operads to capture it already on the beginning? And the answer is yes, we can do it. In the modular operads, we will get enough informations to make there the gluing and self-gluing. And it's because the modular operads exactly have the two kind of compositions. So what is the modular operad? It's a sigma module. So you can think about the vector spaces on which we have some sigma action, the action by the permutation group. Here the modular operad, I denote them, the collection by, I index them by the set C, which is in general some finite set, which can be unordered, and by some G, which is a non-negative half integer. There will be some relation between the geometrical genus you've seen before and this G, but I will talk about it in a minute. And I want each of these components with indexed by C and G to satisfy the stability condition, which looks like this. And it's there for some technical reasons. And this structure, this algebraic space, is equipped with three collections of morphism. The first one is telling us what is the sigma action there, how it acts, so what will be trivial and what not. Then we have a composition between two components of this modular operad will produce us some new vector space with some sigma action. And there will be a self-composition, which basically tells us we connect two elements from one component. We get some new component where the G is raised by 1. And these data are satisfied are required to satisfy some axioms. First, that there will be some compatibility between the sigma module structure and the composition, so that will be called the equivariance. There is also like, just if you look just on sigma module, it will satisfy the sigma module structure. And then there will be a lot of axioms for the associativity between these two compositions. So here is, for example, depicted one of them, that you can either compose first you can think about the elements of the modular operator as some kind of like corollas, where you have the set C of the legs, G is like index assigned to the vertex, And when you have these composition maps, you can be thinking about them as like connecting the legs of two corollas, contracting them and getting new corolla. So this is a picture you can have when I'm talking about the modular operads. And the axiom, which is saying you that you have the associativity between the composition maps, then tells you like, I can first compose two legs of two corollas, and then on this new corolla which I get, I can make the self-composition where I connect two other legs. Or I could do it the other way around, that I first compose these two legs indexed by A and B, and then I do the self-composition C and D. And then there are a few more axioms telling me the associativity. And now it seems that what we had here is like what we want. We have some composition as before, but there is a problem to have the full BV algebra. On the modular operad, I don't have anything like a product. You don't see here anything like this. And if I want to take the idea that everything is already encoded in the modular operad, then I have to somehow equip this structure with something like a product. So this is where we came with the idea to make the connected sum. And the connected sum, basically, the modular operad with the connected sum basically is that you take the modular, as you've seen now in the previous slide, and you add there two new maps, two new degree zero chain maps. And the one of them is basically taking two components and producing new one where you raise the grading G by 1, and the other one is basically just raising the grading by 2. And there is a lot of axioms. Now I just listed first 3. There will be another slide full of axioms. And these first 3 are basically telling me that similarly as I can see the modular operads as algebra over some monad, and I can describe it purely categorically, I can do the same with the connected sum. So if I have some sigma module equipped with the connected sum, then these 3 axioms are telling me that I have the algebra over the monad. And these other axioms are basically telling me that if I have the modular operad, which is one algebra over one monad, and the connected sum, which would be another algebra over other monad, another monad, then there will be like some compatibility between these two structures. And basically the axioms are telling us what we would naturally expect, like how to exchange the order between like what we are doing in the connected sum and what we are doing in the modular opera in the composition. And now everyone could be like, okay, it's a lot of axioms and I have no idea what she's talking about. So a geometrical picture which you can have is very nicely seen on the examples. So the basic one with the closed modular operad is, for the closed strings, the operad which is capturing them is called quantum closed modular operad. The notation is kind of obvious. And the sigma module there, the strange collection of vector spaces, they are just one-dimensional for every C and G. So C is here some set of the punctures, and G, big G, has some relation to the surface of the Riemann surface I was talking before, and the relation is given by this formula. So the big G is given like twice the geometrical genus by plus something. And when you look on what the connected sum is doing, it's really doing what you would expect from the topology. So you take two surfaces and really glue them together. So you can think about like attaching there some cylinder between two surfaces, or that would be for the connected sum between two components, or you can think about gluing a new handle on the bulk of one surface. That would be the connected sum on one component. And as you can see, we have now the consistent grading. The big G is really raised by 1 for the two surfaces and by 2 for one surface. And so we are consistent with the closed case. That's good. And now, is it making our open case working? And the answer is yes. So if we have the modular operad, which should capture the open case, then we have a set O of all punctures. And I will say that there is a cyclic word, which means that I have several distinct elements of this set, and there is a cyclic. If I act by cyclic permutation on this word, it will be trivially the same. And then each component of this modular operad will be indexed by this set O and the big G, and it will be spanned by the elements of this form, where O1 up to OB are these cyclic words. Each of them is assigned to one boundary. So here, for example, on the picture, you have the cycle O1 on the one boundary, O2 on the other boundary. And as you can see, we also allow the empty cycles. And the G is this time, the big G is this time given by twice the geometrical genus, but plus number of the boundaries minus 1. And the connected sum works again as in the topology, that you just glue two surfaces together. So you basically take two surfaces, add them, and then you add the generas, and you get a collection of all cycles of all boundaries. And the connected sum on one component will basically just raise the geometrical genus by 1. So it's again acting as you would expect. And of course, you can combine these two cases to open-closed version. So you will have the open-closed modular operad, which is technically a two-colored modular operad. So there is like some subtle technical detail, but it is what you would expect. You get the homomorphism classes where you have punctures on both interior and on the boundaries. There is like some sigma action on the closed punctures and sigma action on the open punctures. And the connected sum just works as here, that you just glue two surfaces together. And as I already showed on one picture before, what we are actually doing is that we have the operad morphisms, but we have the operad morphism from the Feynman transform of the modular operad to this chain complexes or to this endomorphism operad. But because it's Feynman transform, it's actually not just a modular operad, but it's somehow twisted modular operad. And for this twisting, one can think of a similar construction as with the normal operads, that you have the cover complex, and there must happen something with the changing the degree, so you shift somehow the space. But with modular operads, there is a technical problem that just shifting the space will not save you, because there is that self-gluing, and for that you need to really think about like little different construction, which is called Feynman transform. And basically, it says that you need to somehow modify the composition maps. So I will consider a vector space with odd symplectic form, which will be of degree -1. It will be compatible with the differential. I will use this later. And the odd modular endomorphism operad is then you take the collection, the sigma module will be given just by the tensor powers of the vector space. Here I consider just the graded dual. And the structure maps, the compositions, are now of degree 1. So you take two elements, F and G, and you basically you use the pairing from the symplectic form. So it will give you a function which will be of, the composition will be of non-trivial degree. And similarly, on one function, you use the self-composition, where you again plug inside the elements AKs from homogeneous basis, and AK with the upper index is just given from the pairing with the symplectic form. And now for this odd modular endomorphism operad, I also want to have the connected sum. So when you check, what will happen is basically that on one element, the connected sum is, on the first side, it seems that it gives me the same thing, but don't forget, it's formally an element with a different grading G. So I raise the grading by 2. And on two elements, it seems like a standard concatenation product, but again, I am raising the G by 1. So they are formally in different space, just they seem the same because the space looks the same way. And yeah, and now when I have the normal differential graded modular operad P, and there are all components n and g are finite dimensional, then and I take another modular operad, which will be odd modular operad, I can consider the space which will be given by the tensor product of the components of both operads, and I will consider the diagonal action and take the invariance of this space. So this is this first line. And then when I make a collection of all these into the direct product, I get something which I will call fun. You will see that later they will give us the formal function, so it will be called fun PQ. And on this space, I have naturally a differential given by the differentials from both operads. I get the Laplacian, which will be of degree 1 as we want, because here the composition from the operad P is of degree 0, but the composition of the operad Q will be of degree 1. It's the odd modular operad. And we will have also the bracket, which will be given by the composition between two components. So then I have these three things, and as one can check, there is like this compatibility. So D will be really the differential. Maybe here should be the big D. Yeah, the big D. There is some compatibility between the differential and the bracket. The Laplacian is square 0, and there is some compatibility between the Laplacian and the bracket and the differential. And also the bracket satisfy a graded Jacobi identity. And what one gets, and already was done before by others, one gets the generalized Batalin-Vilkovisky algebra. And because we introduced this connected sum, we are now able to introduce also the product. So the product will be given on two components by this connected sum on two. The first one is from the operad P, and the second one is on the operad Q. So I consider there on both of, I need to have a connected sum on both operads. And we also introduce the operator called sharp, which will be just the connected sum on one component for both of these operads. And then the theorem is that what we get on this space with the D plus delta and the bracket and this new product is a Beilinson-Drinfeld algebra. So it's nearly the same as the Batalin-Vilkovisky algebra. So we get the graded commutative associative product on the element. It looks like this. We get the identity between the compatibility between the bracket and the product as we would expect. But there is something different in the compatibility between the Laplacian and the product. And what is different here is that here we get this sharp in front of the bracket. And the reason is that, as you have seen, the star will raise me the grading G by 1 and the Laplacian also. So the left-hand side raised the grading G by 2. The first term raised it also by 2, the second also by 2, but the bracket wasn't raising. So we need to use there the sharp operator to raise the grading in G the same way to have the formally correct equation. And when one has this space and the connected sum 1 is injective on the operads we are considering. So now we can restrict to some general operad, modular operad P, and instead of Q, you can now think just about the odd modular operad for endomorphism operad. So just the endomorphism operad as I showed you. Now we can introduce the space of formal functions where we take the fun of P with the endomorphism operad, we tensor it with the formal Laurent series, and we factorize it by the relation which is given basically by this. So here I introduce the Laurent series in variable kappa, and I identify the positive powers of kappa with having the sharp operator there. So whenever I have the sharp operator, I can exchange it for the kappa powers or other ways around. And now I can introduce exponential. Technically, I should say that I have also completion of this. And then I consider the exponential, which will be the element which is given like this. So I think about the sums where I use n times for every component from 0 to infinity. I will have n times the product of the element x. And to have really exponential as one would expect, I would need something like 1 on the beginning. But modular operads, because of the stability condition, doesn't have anything like 1. So we formally add here the element 1 as a generator. And when we add it into the component n is equals 0 and big G is equal to -1, it will really act as the unit for all our operations. And one can think about what does it mean that we add the generator in this space. And if you think about both our examples, it actually means that if this is -1, that genus is equal 0 and there is a 0 number of boundaries, or in this case, the same way that there is a 0 number of punctures. So basically it means that we add something with 0 number of punctures, 0 number of boundaries, and the genus is also 0. So it's actually a sphere. So we added something naturally fitting into the picture. And now in this space, we can think about, like, we can use actually the results of Batalin-Vilkovisky, because if we think about what is the Feynman transform of some modular operad into the endomorphism operad, so the representation of this Feynman transform, we can equivalently give this operad morphism as a degree 0 element of this space of functions, which I showed you. And this element should be degree 0 and order 0 in kappa, and satisfy the quantum mastery equation, which basically means that we have this equation. It's kind of different from the quantum mastery equation I showed on the beginning, because there is no h bar or kappa in this equation. And if you look on what it means for each component n and g, where you satisfy the stability condition, then basically this relation is telling you that you should have this for every component n and g. And if you look closely on what does it mean, it basically says that this is equivalent to say that exponential of this element of s over var kappa is d plus delta closed. So we found that the elements which are describing as the Feynman transform, the representation of the Feynman transform, are basically the same as those who are in the exponential d plus delta closed. And similarly, as for the closed case, we will call the structure which is described by this as the quantum homotopy algebras. So now we have the structure on some vector space, and one can ask if it's possible to do the same things as with the closed case, where you can take the quantum L infinity algebra and transfer it to the cohomology, or in other words, you can construct the minimal model. And it's possible also to do it here. So if you, it's kind of like a general way how to approach this is that usually you construct something like a homotopy retract, and then you have some techniques how to transfer it to the cohomology. Here we use a special situation where we have a special deformation retract. So we will have the vector space with the differential D and the other chain complex W with differential E. And we have like pairs of quasi-isomorphism between them and some homotopy on the vector space V, such that they satisfy all these conditions. So basically it tells you that P is a projection, E is inclusion, and you have this relation for the homotopy. And the special, in the name of special deformation retract, basically means that you have these three conditions. And in this case, what we are doing is that we want to construct the minimal model, which says that we want to see if it's if there is a quantum homotopy algebra on the cohomology, so it's useful to consider the Hodge decomposition, where exactly you get the original vector space and split it into the cohomology with respect to the differential, plus two other components. One of them is given by the image of the differential, and one is the rest which you get there. And if you consider the basis of these vector spaces, then you can split the symplectic form, thanks to the fact that we have the compatibility between the symplectic form and the differential. So you can split the symplectic form, and so you can also split the Laplacian into the part which is just on the cohomology and on the rest. And the same way you can split the bracket just to the part which is on the cohomology and on the rest. And then by transfer trick, you can take these components, these vector spaces, the cohomology and the rest, and basically introduce the special deformation retract also on like the tensor products of these components. We assume here that the differential on the operad is trivial, and in most cases one consider this condition is satisfied. In the closed strings, we consider the quantum modular operad, a quantum closed modular operad, and that one has trivial differential. And the same way on the open strings, we consider the open modular operad, and that's also, the differential there is also trivial. So we have this special deformation retract where we have the functions on the vector space and the functions on the cohomology. And now, because we are in this special situation of special deformation retract, we can use the homological perturbation lemma. And it's kind of like a helpful tool to use on the special deformation retracts. You just consider a perturbation, which should be a linear map of degree 1, such that the original differential on the vector space V plus this perturbation squared is a 0. So, and you also consider it small in the sense that you can think of this sum. And then if you consider this perturbation, you get a special deformation retract, which means if you consider this perturbation, so you will have the vector space with the differential which is perturbed by this perturbation, you get again the special deformation retract. So you again get some two chain maps, P, comma, I, comma, and some new homotopy K, comma, which are given by this perturbation this way. So these four equations are telling me how they will formally look like. And it's again a special deformation retract. So I again have the compatibility between the P and K and others. And we can use it in our case. So we have the functions on the vector space and the functions on the cohomology. And we can use as the perturbation, the BV Laplacian. It satisfies exactly the condition we want from the compatibility with the differential. And then if we consider what we had before, like we showed that there is some quantum homotopy algebra on this vector space V, on the functions on the vector space V, and we can transfer it to the, we can try to transfer it to the quantum homotopy algebra on this cohomology. So the quantum homotopy algebra on the vector space V was encoded by some element S, some action, and on the cohomology it should be encoded by some other element. We call it effective action. So the effective action will be element on this, in this formal functions, which will be given by the projection of the exponential of the original action and multiplied by kappa, or like there is this relation. And the theorem which we proved is that this effective action is well defined. So there really is something like this. And if we start with the action S, which was degree 0 and order 0 in kappa, the effective action will be again degree 0, order 0 in kappa. And it satisfies the quantum master equation. So we will get equation which is this time given just by the Laplacian on the cohomology and the bracket just on the cohomology. And because it's the cohomology, we don't have here the term for the differential. And now one can ask if we have the two elements which are, if we have two actions or two Maurer-Cartan elements, the solutions of quantum master equation, is there some relation between them? And usually for like saying that two things are homotopy, you want to connect the two elements by the family of objects of the same type, such that you can parameterize them by something. So for this, we introduce the homotopy this way, is that you have some combination of elements AT, BT. The parameter T is like basically the parameter of the homotopy, and they should be from the formal functions times the Derham complex on the interval 0, 1. So, and this collection or this family of the elements should tell you what is the homotopy between the element A0 and A1. And we say that there is a homotopy if AT is of degree 0 and BT is of degree -1, and if there is this condition satisfied. So you say that similarly as before, the exponential of this element will be d plus delta plus the differential of the Derham complex closed. And then the theorem says that if you have two actions of 0 order in kappa, then there is equivalent condition to this homotopy, and that's that there exists element f such that we have this relation that the exponential of one action, the exponential of other action is d plus delta of this element f. Here is one remark to this, is that this f doesn't have to be of the, we are not saying that the A and B are of order 0 in kappa. So we are connecting the two actions which are both of order 0 in kappa, but we are going also through the elements which are not of order 0 kappa. So we are connecting them by something which satisfy the d plus delta, that they are d plus delta closed, but we are not saying that they satisfy the quantum master equation, which is equivalent condition only when we have the 0 order in kappa. So then we are able to construct a homotopy between the original action and this effective action. So we are saying that there is like some way how to think about, there was like, if you think about the original action as on the whole space V, and this effective just on some Lagrangian subspace, then we are able to like say that it was possible to connect them. And then we want to say that if you have two solutions for two vector spaces U and V, then we want to say that we want to introduce a morphism between these formal functions on one vector space and for another vector space. And the morphism which should transfer the quantum homotopy algebra from one to another should be compatible with the Poisson bracket, or with the bracket this way. So we are saying basically it's Poisson. And if we have two elements from one space, the U where we are starting, then this map should tell us that if we act by this morphism on the delta plus S of f, then we get this right hand side of the equation. And then if we assume that there is Hamiltonian flow given by this from the BT, where BT was given from the homotopy, then we get a third equivalent condition to our homotopy, to our definition of homotopy, and it's that if we have the element in the formal functions such that we can think about phi1 as this element, then the Poisson is a Poisson map. Then phi1 is a quantum homotopy algebra isomorphism between the formal functions on the vector space V with the action as a 0 and the formal functions with the action as a 1, if and only if there exists the homotopy in the previous sense. So there is something connecting as a 0 and as a 1. Yeah, and this is all.
Okay, so let's thank our speaker. If you want to unmute yourself, feel free to clap. Okay, so fantastic talk. I'll open up for any questions from the audience.
Okay, can I actually ask a question? Hi.
Hi, yes.
Hi, so I will ask probably something what we were discussing here, but maybe it's interesting for the people. So if the symplectic form, because in applications, it's not usually, things are not usually of degree 1. So if, for example, you have something of degree D, so does the theory changes much, or what is going to happen? So this is a first question. And another question, your product, connected product, the new product, increases genus by 1, right?
The grading G, yes.
Okay, good. No, because, yeah, okay, good. Because somehow my idea is that also the reason why you divide in the exponential by the parameter is because in the action you somehow sum up in the application of string field theory, you sum up algebraic vertices times the corresponding genus of the surface, and somehow if you then compute the exponential, then somehow if you have a product s over h times s over h, then the genus of this should be g1 plus g2 minus 1, which corresponds to 2 times dividing by h and 1 times increasing by the product, right? This is the correct intuition.
Not sure now. Like the thing which we are doing when we consider this equivalent relation is that we are saying that we can exchange the positive powers of kappa for the connected sum, which is raising the g by 2, but we cannot do it with the negative powers. So when we have the exponential, which we consider most of the time, where we have 1 over kappa, then we cannot exchange this for the genus. There is we are not saying that we can like have something like a negative genus. And because we have the stability we always have the stability condition, which basically restricts also this. So we know that the big G must be non-negative integer, and we know what is the relation between the geometrical genus and the big G, and we have the stability condition, so we never can get to the negative geometrical genus.
No, but the geometrical genus can be also negative if you have, for example, a disjoint union of spheres.
Yeah, but what our connected sum is doing is that we really get something which is already somehow like connected. So we don't have the disconnected elements.
Okay, but the connected sum has increases genus by 1. This degree, this kappa. Okay, good.
The connected sum, like on 2 components, is the geometrical genus is still the same, and on 1 component is raising by 1 the geometrical.
Okay. Okay. Okay, and the second question was the degree D of the symplectic form.
So when we have the symplectic form of different degree, it basically tells us what is the degree of the composition. So if we want to change the degree of the composition here, it would mean that we have a Feynman transform which is like somehow shifted, in the sense that we started not with a modular operad, but with already twisted modular operad. And then the Feynman transform gave us some, again, twisted modular operad of different degree. So here the odd is a special case of twisted modular operad. And if we consider a symplectic form of different degree, then it would mean that to get a Batalin-Vilkovisky algebra or the Beilinson-Drinfeld, where we have the delta and the bracket of degree 1, we need to compensate this in the modular operad. So when we have this combination of P and Q, it would mean that if you have here the composition, the black bullet of some degree D, then the bullet for the operad P must be also of some degree, and it must be of degree D minus 1 or D plus 1 or minus D plus 1. So you then compensate what you had in one composition with the other composition to have really something of degree 1. So you need to start with different, like you don't start with just modular operad, but with twisted modular operad, if what you mean, if that's what you mean.
Okay, good, okay.
So
Because,
oh,
yeah.
sorry. No, I just wanted to comment that Baranikov does his theory actually also for different degrees of omega. So what would change would be the part concerning the brackets and the delta. But I guess we can connect it some exactly in the same way, because this is degree 0 always, right?
Yes. The connected sum in even in
this
the
will remain probably the same.
Yeah.
So I guess would be just kind of combination of what we have with this more general statement of Baranikov.
Yeah.
Okay.
But maybe Lada, you can also explain this shift in G because and the choice of the G.
Like,
because it is kind of convention, right? Because we use some particular convention.
Yeah, like when one looks on the combination, how the big G is given from the geometrical one and from the number of boundaries, like in general, there could be like any alpha here. There doesn't have to be exactly 2. And then there would be like some coefficient in front of the B, which will be also given by some alpha, and the number of the punctures will also play the role. So it's possible to have here some different linear combination, and we choose this one basically just because Zwiebach already set this convention. And in the open case, it's what we were once discussing, is that when you have the ribbon graph, the big G is basically by this formula giving you what is the fundamental group of the ribbon graph. But for the closed case, there is not this convention. We don't know about anything which would be like half integer of something, and it would make some topological sense, like in the open case. So we have some convention for the G, which is given by Zwiebach. In general, we could have some different G, and if we decide to have just multiple 1 in front of the geometrical genus, we basically can change the connected sum to have the connected sum on 2 components by just adding the 2 big G's, and on one component rising by 1. So this +1 +2 is because we choose this convention which was given by Zwiebach. But in some cases we can decide to have different convention and get rid of this adding +1.
Mm-hmm. Does this convention have? Yeah, sorry.
No, please go. Please go.
Does this convention have any meaning? Because this big G is a number of loops, right? We also discussed this of this ribbon graph. So if you have a ribbon graph, then then somehow the formula for big G is the number of independent loops in that. And so is there somehow lurking in behind some relation of quantum field theories and string theories, you know, because somehow the modular operads are sort of so the motivation which comes from Zwieback. So is it somehow like this, that this big G appears, or that the modular operad is graded by this big G and not by small g, for example? I mean, yeah.
I don't know if there is like some good explanation behind the whole quantum field theory. I know that he chose it because of some, not sure what was exactly the motivation, but he chose some convention. And
so maybe this is a good question for the audience. Maybe someone knows, because we or Lada in her talk avoided to use H bar, but you can introduce it. You can introduce H bar as a bookkeeping parameter and get it in the same places as it is usually, in addition to our kappa, which has a different meaning. And then this normalization of Zwieback, it essentially says that you have in the action, in the interaction part, that the vertex, the open vertex, just a disk with 3 punctures, is of degree 0 in H bar.
Right.
Which, well, this is the classical thing, right? Just disk with 3 punctures. So you would take the first one, interaction. So it's natural. But then the sphere with 3 punctures in the open closed theory has degree H bar, I guess, to 1/2 or something like that.
Okay.
But well, you could choose it also the other way around probably, and well, because there is this freedom in, well, you can shift that. Yeah, there is this extra parameter which enters kind of linearly.
But a sphere with 3 punctures, is it stable?
Oh
yes,
yes, it is. It is. So it has something, you know, probably to do with the fact that if you consider full open string kind of string field theory, including open and closed strings, that somehow the closed string is already like kind of quantum effect coming from the point of view of open strings. And it may have something to do with the fact that people say that you cannot have just consistent quantum string field theory for open strings, that you must include also closed strings. So maybe this is one reason for this kind of normalization, which tells you that, yeah, in the quantum case, if you have open strings, you need also closed. So I don't know, maybe someone knows a good explanation for that. Because Zwieback in the paper, we didn't find kind of explanation of why he chooses this normalization.
Lada, I have like a very naive, simple question. I got a bit lost. What is this kappa, and how should I be thinking about this kappa?
So we want to.
It's not a H bar parameter or anything like this.
It's not H bar. Like usually people use H bar to somehow say something about the genus grading, or like they want to somehow capture that there is a genus. And when you have just the closed strings and the formal functions there you have just the symmetric powers of the tensor of the vector space, and then you don't see anything like a genus there. So they added there the H bar to somehow hold there the information about the genus.
Right.
But we have the information about the genus there. It's in the big G, and we add the kappa there because we want to consider the elements where we have like 1 over kappa for later, because the quantum mastery equation corresponds to the case where we are like considering e over exponential of s over var kappa, and this would be d plus delta closed exactly in the moment when we have quantum mastery equation. So we want to consider the quantum mastery equation or these properties in this space where we introduce the formal parameter, because then it's consistent. But the kappa is not exactly the same like the genus, because in the formal functions we can add there any possible powers of kappa, and they would be independent of the genus. We can exchange them for the connected sum and artificially raise the genus, but we can think about like any element of this space.
Right. Okay. So it's some formal parameter that
Yes.
you're like a yeah. Okay. Yep.
Because then the exponential makes sense only when we consider like 1 over the kappa, s over kappa.
Sure. So it's in some sense it's like a bookkeeping device. It's just used to kind of keep track of things. Is that right? Or
Yes.
does it have
exactly.
more some more fundamental meaning, or is it?
Well,
I think
of,
it's more like a bookkeeping for the computations.
Okay.
Like in when we are later proving that the effective action, like when we are proving the effective action on the cohomology, we are able to use the same arguments as in the normal quantum field theory. And then basically what we are doing is that we have the surfaces which are decorated by some elements of the vector space. And each of these surfaces has assigned, is like, for every vertex we assign like 1 over the kappa. So when we connect two surfaces, we basically get rid of this kappa just by what the combination of the homotopy and the projection is doing, like what the propagator is basically like delete this kappa. So then we again get every component will have just like 1 over kappa, and basically we are somehow like keeping there the information that every component is just 1 over kappa.
Yeah. Okay. Yeah. Okay. Very good. Yeah. Awesome. Thank you.
Lada, maybe also like a question. So now it's somehow becoming clear. So if you want to do like open string field theory with this, so you have some collection of algebraic vertices, you want to construct a BV action. So you basically have for every genus G surface with some boundaries, blah blah blah. You have some algebraic term in the action, and genus G surface gives you kappa to the G times some element of the rest, right? So some and all the operations, even the bracket, what you do, the powers of kappa in front of the coefficient correspond precisely to the geometric operations which you would be doing on the side of this topological category. Because I mean, string field theory is some functor like monoidal functor or whatever. So you can always, and the BV operators, they also are somehow shadows of some BV operators on some, if you imagine like really connecting worldsheets and so on. So the power kappa to the G in your formalism always corresponds to the genus of the operation of the surface which is on the topological side. Is it true, this statement? Or
not exactly, because we can exchange the powers of kappa when we have there the connected, when we have there the sharp, the connected sum acting on one component. But when we start with the surface where we didn't use this connected sum, this sharp, or we didn't use the kappa and it has some non-trivial genus, then we cannot like exchange it like trivially. So just having non-trivial genus doesn't mean that we have used either of these two things. So we cannot just get rid of the genus by kappa. We are saying that we have the relation between the kappa and the sharp. But if we start with the genus which has some, with the surface which had some genus, it doesn't mean that it doesn't imply that there was a this sharp So it doesn't mean that we cannot, it doesn't imply that we can exchange it for var kappa.
No, but this is somehow the input of the ad hoc input is that you input the contributions of the surfaces with the correct power of kappa at the beginning, and then your formalism somehow keeps the correct power of kappa under all these operations, right? I mean,
yes.
Yeah. Okay.
Yes.
Okay, I might just stop the recording here, and then if anyone wants to ask questions after that, they still can.